Okay, so recall that we are in chapter 5. If you haven't started looking in the book yet, remember that these notes only say a third of what I am saying, and I can't tell you everything that you need to know. There's a whole wealth of information and understanding that can be helped by reading in the book. So make sure that you read this material too. All right, so what we're going to try and do today is define energy and some terms related to energy. So get you started on your vocabulary. We want to make sure we're looking at the units used for energy. So these are units that don't usually end up in everyday life the way that grams or meters might. And we're going to look at some different types of energy and how they relate to chemistry. And then we're going to describe how energy moves or is stored in chemical systems. Okay. So that's just kind of where we're starting out. So this unit is on thermochemistry. The thermo part means heat. Chemistry, of course, means heat. It comes from thermodynamics. And thermodynamics refers to the changes in heat. So dynamic means change. A dynamic character in literature is changing over the course, developing and growing. So thermodynamics is the changes in heat. As it's thermochemistry, we're specifically looking at chemical systems. In chemical reactions, there is always going to be some kind of change in energy. Now, sometimes that change in energy is very small and won't really be measurable, but there's always going to be some kind of change in energy because energy is created every time we form bonds. Energy is used up every time we break bonds. Or do we still need this slide? Okay. So what is energy? Let's make sure we're talking about the same thing, because sometimes when we have a word that we use in everyday life, it doesn't mean exactly the same thing in chemistry. So in chemistry, energy is something that allows us to either do work or to supply heat. Well, again, work and heat are terms we use in everyday life. So what do we mean by those? So in science, work is moving a mass over a distance. So a force times a distance is how physicists are going to calculate work. For chemistry, usually this involves having a gas that is created, and that gas expanding is going to be moving the air particles around it, or if it's in an engine, it's going to move a piston or something like that. We won't focus too much on work. We'll think mostly about the heat, but chemical systems can do work. So heat is the transfer of thermal energy. And thermal energy is the kinetic energy of the molecules. So when we are transferring thermal energy, we are causing a set of molecules that are going really fast to bump into molecules that are going slower. The slower ones speed up and the faster ones slow down. So we are transferring that kinetic energy from one set of molecules to the other. Are we good on this slide? All right, so together these two terms, heat and work, and we represent heat with a Q. Don't ask me why. Chemists are weird. Q and work W together are equal to are internal energy. So, and because they represent changes, work is moving something, Q is transferring heat. They're going to be equal to the change in the energy of the system. So if both of them are positive, of course, my change in energy is going to be positive. If both of them are negative, then my change in energy is going to be negative. But if I have one of each, it depends on the relative size. Now, for chemical reactions that don't involve gases, the work is so minimal that we really just say Q is where the internal energy is. We really focus on that. And most of the things that we do in lab are solution chemistry. The reactions are going on in water. They're not going on in gases, aside from the last 3 weeks. We will focus more on those things. But the total internal energy, yes, the total internal energy is going to depend on both. And you have periodic. So it looks like Dr. Hamilton. Okay, so normally, even starting in grade school, we'll classify energy into 2 categories, kinetic and potential. But because it's going to come up at the end of the semester, I'm going to put in a 3rd category we sometimes don't talk about. So kinetic energy is the energy of motion. In physics classes or in middle school science classes, we often talk about, oh, there's a car moving down the road and it weighs this much and it's going this fast. But also molecules are going to have kinetic energy, and we think of that in terms of thermal energy or heat. And then also anytime there's a sound, that's causing vibrations in the air, which causes your eardrums to vibrate, which sends that onto your brain. So sounds are also a kind of kinetic energy. And I haven't listed all kinds of kinetic energy, but I just want to make sure that we are thinking about those as well as the more obvious things. So the picture here, if you can't tell what that is, it's supposed to be rushing water. We've got a river going through there. That's kinetic energy of the water. Our second kind is potential energy, and this is stored energy. So if you've had physics, we usually talk about something being up high as having potential energy because it has the potential to fall or to move. We also can talk about elastic potential energy, and that might be for a spring. So if I stretch out a spring and then let go, it's going to start moving. It's going to collapse. If I squeeze a spring, depending on the kind of spring it is, but if I squeeze a spring, then it'll straighten out, or not straighten all the way out, but expand a little bit. So that's elastic, as is rubber bands and the elastic in the waistband of little kids' pants and things like that. And then the one that's most important to chemistry is electrostatic. So if I have a positive and a negative charge, they want to get together. And as long as they're not together, they have the potential to get together. So there is potential energy in that. And chemistry is all about trying to minimize that potential energy, minimize the possibility of the particles moving from where they are. And then in our last chapter, we'll talk about radiant energy. Sometimes people throw this into kinetic energy because we've got motion of waves, but it's not, light doesn't have mass, so it doesn't fit into that kinetic energy really easily. But radiant energy is any kind of electromagnetic energy. Normally we think of that as light, So visible light or ultraviolet light. Ultraviolet light can cause tanning, it can cause sunburns, but also things like X-rays. That is also electromagnetic radiation. That is also energy. Infrared, that is also electromagnetic radiation. It is also energy. Sometimes people talk about IR energy as heat. They're not exactly the same thing. Heat can cause or be caused by infrared radiation, and that's why there's that connection. And then microwaves. So we're familiar with the idea of heating food with microwaves. So that is a form of energy. We can change from the radiant energy of the microwaves to the thermal energy of the food molecules. All right, are we good on this slide? Okay. So I've mentioned a few of these, but since this is a chemistry class, just to remind ourselves how all of these ideas fit into chemistry. Thermal energy comes from the kinetic energy. Every time you see Ke, that's kinetic energy. The kinetic energy of the atoms and the molecules. Okay, so any kind of thermal energy reference is referring to, I've got molecules that are either traveling through space like gas molecules, or they might be wiggling, vibrating. And that might be like a solid where they're sort of locked into one position, but they're wiggling around. My sister has a 5-year-old, and so she calls that the yayas. Her 5-year-old has the yayas and has to get his yayas out by wiggling. So solid atoms and molecules have yayas. All right, so potential energy, we talked about having the positive and negatives. We have electrons being attracted to the nucleus, so that creates a certain amount of potential energy, and we'll talk about that in chapter 6. And then also we have cations and anions are attracted to one another, and that creates some potential energy as well. And then we're going to spend a lot of time in chapter 6 talking about how radiant energy can interact with the electrons in an atom. Different kinds of radiant energy, depending on how much energy is there, can cause the molecule or the electrons to do different things. Visible light will cause those electrons to move a little bit further away from the nucleus, and ultraviolet light even further than that. And then X-rays will cause them to move so far away that they actually break the bonds. And then something I'm going to try and say as many times as I possibly can, forming bonds releases energy. So often people think the opposite is true. And I know where the misconception comes from, but I'm not going to address it. So forming bonds releases energy. So we've got terms related to heat, thermal energy and temperature and heat. So it's important to remember that temperature and heat are not the same thing. Usually heat is going to cause the temperature to rise, but if we have a phase change, if I'm melting ice, I can apply heat, heat can be absorbed, but I don't change the temperature, okay? I just go from ice at 0 degrees Celsius to water at 0 degrees Celsius. Okay, so what are the differences? So thermal energy is the motion of the particles, and temperature is how we measure it. You might think of it in terms of like a racetrack is where people do their running. but distance is how we measure how far around the track they go. That distinction isn't so important to me as between temperature and heat. So temperature is what is this one particular material, substance, object. Okay, so it is static, one point in time, what is the temperature? Heat is the transfer, so it involves a changing situation. The heat was here, fast molecules over here, now we're going to move that heat over here. Heat is always transferred hot to cold. So a lot of things in chemistry are reversible, but this is one that is not. And so this is part of a concept of entropy, which is sometimes called times error, which says we know which way is forward in time because we know that hot things are going to transfer their heat to cold things. So if I was looking at a film and it had thermometers of two things sitting right next to each other, and I saw this thermometer getting lower and this one getting higher, and they're getting separated in temperature, I would know that film was running backwards because two things next to each other are going to equal out one another. All right, units. So we have heard the term calorie. The way we use calorie with food is not the way we use it in chemistry. Technically, it is the energy required to heat 1 gram of water 1 degree Celsius. So you can imagine that's not very much. 1 gram of water is a few droplets. And if you put a few droplets of water in your hand, they would rise in temperature several degrees, probably, unless they're already warm. So what we normally are talking about is a food calorie. Notice this is capitalized here. A food calorie is actually a kilocalorie, which means how many calories? What is kilo? It's kilometer. 1,000. So a kilocalorie is 1,000 regular calories. So when you're eating something that is, 5 calories, you're like, oh, this little cracker is mostly air. It's only 5 calories. It's actually 5,000 calories in chemistry. So it's something to be aware of. So we used to do a lab that involved finding how many calories were in a piece of food. You had to put in that conversion in there in order to get to the food calories. The one we will use more commonly is the joule. So both of these are metric units. Both involve degrees Celsius, but the joule is based on the SI unit. So that's Standard International. It's a French term that I can't pronounce properly. And so that's where it comes from. You don't need to know this formula, but this is just the term, this is just where it comes from. The reason I point this out is that we are going to use this to come up with a different version of the gas constant. So in the last chapter, we used R and we had 0.08206. Now we're going to have a version of R that's going to show up in various chapters for the rest of the year. That's going to be 8.314, and it's going to have joules instead of liters atmospheres. Okay. So what happens when we have heat transferred? So the kinetic energy of the hot molecules is going to be transferred to the cold molecules. So we have here on the left in red is the hot molecules, and to the right of that in blue are the cold molecules, and they sort of indicated with more lines farther out from the circles that is more energy, and then these lines are really close and there's fewer of them. So these hot molecules, as we bring these two objects together, right at the border, they're going to start bumping into each other, and the hot ones are going to be slowed down by bumping into the cold ones, but the cold ones are going to be sped up by bumping into the hot ones. And so that heat gets transferred from the hot to the cold until they reach what we call equilibrium. So thermal equilibrium is when we have two things that are the same temperature. All right, so that's visually what it looks like. So first, the hot molecules are either heavier or moving faster. That's what gives them more kinetic energy. And as they collide, the hot molecules are slowing down and the cold molecules are speeding up. And the transfer between the two is going to stop only when we have equal temperature on both sides, thermal equilibrium. So next week in lab, those of you that have lab, you are going to have a piece of metal that you are going to have very hot, and you're going to put it into room temperature water. So you know that the hot metal has a lot of energy that it can transfer to the colder water. So the molecules at the surface are going to be bumping into the water around it. The water will mix around so that it is able to transfer that heat throughout the water. For the metal, the molecules that are, or the atoms that are on the inside are still moving pretty fast until they bump into the now slower moving ones at the surface. So it's a little bit of a slower process for the metal. So it'll take a couple of minutes, but we're going to basically do this idea in a lab. So how are we going to measure that? And I think that's the next slide. Are we good on this slide? All right. So how do we measure the heat? Heat is what is transferred. That's the energy change. And every material can absorb heat because everything has atoms or molecules that can go faster or slower. So we talk about two things. One is heat capacity. And this is generally when we're talking about a whole object. So we might say the heat capacity of a thermometer, or the heat capacity of the entire oven. In lab, you'll say the heat capacity of the whole calorimeter. Usually that object is made up of more than one thing. So your thermometer has the glass, it has the ink that marks the lines, it also has alcohol in it if we have one of the analog ones, or it has the piece of metal that you put in, the probe, and then it's got the plastic at the top and the digital display. So it's lots of different things. So for that one, we have to have a heat capacity for every single object if we're going to use heat capacity. We can't generalize it. So what we often use is the specific heat capacity, and that is the heat per gram per degree Celsius. I can talk about the specific heat capacity of water, the specific heat capacity of aluminum, the specific heat capacity of styrofoam, but I can't talk about the specific heat capacity of this classroom, okay? Because different parts of the classroom are going to absorb heat differently. 90% of the time in class, we're going to be dealing specific heat capacity per gram. There is one part of the lab where you need to talk about the heat capacity of the whole calorimeter rather than the per gram, because the calorimeter is a styrofoam cup with a plastic lid and a thermometer, so the different parts absorb differently. All right, now can I move on? Okay, so let's look at some specific heat capacities. It's going to depend on what the elements are, because remember that kinetic energy is related to the mass of the atoms. It's also going to depend on the structure. So for gases, because the molecules are so far apart, they have difficulty transferring heat from one to another until they actually collide. And then there are fewer things that can be moving around. So they might have a different heat capacity than something where all the molecules are really close together. So metals, by and large, tend to be pretty low, less than 1. Non-metals tend to be moderate. And the only great example, or only a couple of examples that are in here are wood is kind of in between. Cement has metals in it, so it's a little bit lower. Glass has silicon in it. Granite has some metals in it. So wood is really the best example of kind of a non-metal sort of thing that has no heavy elements in it. Anything that has water in it is going to have a high specific heat capacity. And this is for 2 reasons. Water is polar. And so the molecules are really attracted to one another. And so that means if I'm trying to move one molecule, I'm also trying to drag along all the molecules that are around it. So I have to put in a lot of energy to get all that motion. Water also has what is called hydrogen bonding. We'll get into that next semester. But basically it has an oxygen and a hydrogen, an OH. And that hydrogen bonding increases the polarity. It's more complicated than that, but we'll just say for now, it increases the polarity. So if I look at ethyl alcohol, you can see I've got an OH here. It's going to do the same thing. Ethylene glycol has an OH here. So anything with an OH on it is going to tend to be higher than the others. So water's super high because the whole thing is just OHs. There's no part of the molecule that's not an OH. And then these alcohols are a little bit higher than other things. And so they're, and that's because they have the OH. Thank you. Questions?
I'm a bit confused on some of these, but I'll ask you later.
Okay. All right, so I think we have just enough time to go through a calculation. All right, so when we measure heat, the transfer of something, what we're going to measure is the mass times the specific heat capacity times the change in temperature. So there's going to be a change in temperature because there is a transfer of heat. Now, anytime you see that triangle, that's the Greek letter delta, that means final minus initial. So it's not just a magnitude of change, it also has a sign, either positive or negative. And that sign tells us, is the energy going from the piece of metal into the water or from the water into the piece of metal? It tells us the direction that that energy is flowing. So we're going to try one quick equation plugging these things in. All right, can I move on? Okay, so here's our problem. Again, we have the equation, Q equals MC delta T. We have a cup of water. There are 275 grams of the water. It starts out at 65 degrees Celsius and it cools down to 24 degrees Celsius. We know from our table, if we look back on the table, not because we memorized it or can somehow divine it, water has a heat capacity of 4.184 joules for every gram and every degree Celsius. So we have 3 numbers, well, we have 4 numbers. So the first thing we need to do is deal with the temperature. What am I going to plug in for delta T? So that's only one temperature. I want the change in temperature. Yeah, 24 minus 65. 24 is the final, 65 is the initial. So final minus initial. Okay, so that's going to give us a negative number. And then we plug in each of those numbers 275, 4.184, and negative 41. And I can't remember if I found that answer or not. Let's see. Yes. Only there should be a negative in front of that. All right, so usually in chemistry, we're going to end up with things in the thousands of joules. Not always, but often. And because that is the case, we often convert to kilojoules. So 2 weeks from now, when you, or not 2 weeks from now, but next week when you do your lab, you're going to have the change in energy is going to be in the kilojoules. Okay, questions? All right. So go back and read section 1 a little more thoroughly now that we've walked through the material in there, and we started touching on stuff from section 2, but haven't really gotten into it. But make sure you take a look at section 1 again now that we've talked about it in class. See if it makes a little more sense to you and if you can get more out of it. All right.